Excellent.
I wasn't going to say
Really tough. No, what is your average? You had to add on an extra like grade just because we were so bad at grammar.
Okay, so we have done most of these already. So at this point, we're just going to take any real questions. And if you don't want to go over it, we don't necessarily have to go over it. So let's see. Let's start with questions 1 and 2. Are we okay with those? Yes, okay.
Yeah.
I mean, we can.
Not the ones we did.
Yeah.
Just do it.
Yeah, but the 2 classes mentioned didn't have.
Oh, that's true. Yeah, it's better.
You have 2 buttons.
Whoa.
The ones that come.
Oh, so one you can write, one you can erase.
Got it.
Yeah, so this is your update.
Awesome.
No, it's a different tablet.
Using a different tablet. Okay, so okay, let's see if the erase works.
I think you're holding down the wrong one. Are you holding down the
Oh, that one's the one.
You usually choose the one with the circle.
I know Miss you use it.
That's select. Oh, that's nice. How about this? What does this one do?
I think you're erasing the white. Yeah. Like there's a white. Oh no, it's drawing.
That's selecting. What is this? Oh, that's a click. Okay. Good to know. No, don't want to delete that. You know what's best to do here is just to start all over again. Okay, so look at question 1. And we have, we've got 1, 1.5, 2.25, 1, 3.375. And it looks like what we're doing, or the rule here is multiply by 1.5. So it seems like we're supposed to multiply by 2.25. So that tells me that this is a geometric sequence. Okay. That tells me that r is equal to 1.5 and the first term is 1. Okay, so let's go ahead and do this. The recursive rule, part A. Recursive rule is A1 is 9. Sorry, A1 is 1 and AN is equal to 1.5 multiplied by the previous term, which is AN minus 1. Perfect. Part B. Part B says, find the explicit rule. Okay, the explicit rule. Any term is equal to the first term, 1, multiplied by 1.5 to the n minus 1 power. You could just leave it like that, or you can simplify that if you want. That's 3 halves to the negative 1 times 3 halves to the n, which gives you 2/3 times 3 halves to the n. That's the way we're dealing with that, okay? Letter C, what is the 9th term? Well, if I'm looking for the 9th term, I probably should use the explicit rule. So A9, that's going to be equal to 2/3 times 3 halves to the 9th power. Now, I don't really know what that simplifies to, but I'm pretty sure you could do that yourself. Okay? D. Use the explicit rule to state if the sequence converges or diverges. Okay, so let's take a limit as n approaches infinity of a n. Yeah, that's equal to the limit as n approaches infinity of 2/3, 3/2 to the n. Note that r is bigger than 1, therefore this is going to diverge. Okay, are we okay with that? R is bigger than 1, so the terms of the sequence keep on growing, not shrinking. If they keep on growing, the limit's going to be 0, or there's not going to be a limit. And part E, find the limit of the sequence if it's convergent. Okay, not convergent, no limit.
Is it okay if we just left it in the first one?
Yes, I said you didn't have to simplify it. Any other questions? How's number 1, okay? Great. Whoa! Okay, should we do 2 as well, or do we have other things to do? We have other things to do. We did 3 in class for everybody, so we're not going to do 3. Question 4, do we need to do?
Yeah.
Yes.
Some of us did it, some of us didn't. So let's take a look at this. Question 4. Question 4, we have a sequence, and it's either going to converge or diverge. So it helps if we look at the first few terms. Okay, when n is 1, I don't remember what we get. We got negative 2/3. When n is 2, we get positive 3, 4, 5, 6, 3, 6. Oh, this might be our pizza. Hello? Okay, I'm going to send someone out there. Great, thanks. Do you have all the money?
Yeah.
Okay. All the monies?
Everybody.
All the monies. Cash monies. Okay, n equals 3. We have 4 over negative 4 over 11. Okay, and let's do one more. 5 over 18. So that's my sequence. Now, there's a couple things to note. And the first thing to note would be this is an alternating sequence. So only 2 things can happen. Either 1, sequence converges to 0, or 2, sequence diverges. Remember, this is only true for a alternating sequence. So let's check if this actually goes to 0. What is the limit as n approaches infinity of the absolute value negative 1 to the n, n plus 1 over n squared plus 2? Yeah. So the thing here to look at is we need to apply the absolute value. And the only thing in this sequence that gives us a problem with the absolute value is this little negative 1 bit right here. That negative 1, can you see where I'm pointing?
No, it's really small.
Sorry. This negative 1 bit right here. Okay. That negative 1 is the only thing that gives me negative terms. So we have to do something about that. Or if I want to take the absolute value, all I really need to do is get rid of that negative 1. Done. That's the absolute value of the sequence. What is this limit? 0. N over n squared, 0. Okay, so does that give us number for condition 1 or condition 2? It's 1. Good. Sequence converges to 0. Good. Remember, there were only 2 options. Either the sequence converges to 0 or the sequence diverges. Hold on, let me look. What is the name of that tool with the spotlight for the mouse cursor? I have to look through all of them. You know, apps for Windows are horrible. There are no good apps.
Probably the utilities folder.
I don't believe it.
Providing the Windows accessories.
Now, I don't remember what the name of that app is. What is that app?
Ask for Tony.
I forced her to go to Bing, or I forced her to go to. Yeah. Okay. We'll figure it out later. Do you want to take a couple minutes to distribute pizza? Yeah, let's go ahead and do that while I figure out this app.
I'll get napkins and you come, you get the pizza.
Everybody's there where you are. It's on.
What is the name of that?
But he was not yet. I
Yeah, I remember what it's called. Nope.
First, I touched my head. Take the space out.
It had it?
Yeah, take out the space. Yeah.
Oh, that's not good. Look where it's attentioning.
Oh, no.
You can take both.
Okay. I'll come back first.
Okay. Street is 3.
You'll be fine. So yeah, another one. Another one. Oh my gosh. You didn't hear them.
Too cheesy.
Did you buy pizza?
Pizza work.
Sorry, give me 1 second.
You gotta start young.
Dalton.
You got 3. Girls like
It's not working. Okay, go ahead.
So we're looking, we're using this rule, and then, okay, so we need to, so we took the derivative here, and I was wondering, we'll look at the graph of cosine, right? It has nothing to do with the graph of sine.
Yeah.
Okay, because it doesn't matter that we started off with sine. Once we take the derivative, now we're looking at cosine.
This is my first time hearing.
In my last time.
Okay. Yeah.
Anyone else?
Yeah, you
Now
can
it's
do
just us and people come by. If you guys want more.
There's some more cheese and some more pepperoni. So.
For number 3, because it's a geometric sequence, so we divide, right? We divide
Yeah,
it.
that's one thing you can do. That's not the only way to do it. That is one way to do it.
But if it was arithmetic, we would subtract it.
How much more is the pepperoni?
That you could probably do it that way. Yeah.
But what's the other way of doing?
Solve for a1, set the things equal to each other.
Okay, and it's gonna be the higher power versus.
It doesn't matter. If you're good enough in algebra, it doesn't matter.
Okay.
What? Where'd you get that?
Okay, let's continue then. Number 4, we kind of did that. Number 5, we did that in class, both classes, right? Number 6, determine if this converges or diverges. That should be pretty easy. Do we need to go over 6 at all?
No.
Number 7, we did in both of them, right? Number 8,
We did that.
we didn't do 7? We didn't do 7. Okay, so some of us did 7, some of us didn't. Let's do 7. We're taking the limit as x approaches 0 from the right of sine x over x cubed. Now this is indeterminate. You'll notice that if I substitute 0, I'm going to get a 0 over 0. So that tells me to use L'Hopital's rule. So let's use L'Hopital's rule. We're going to take a limit as x approaches 0 from the right. The derivative of sine x, cosine x. The derivative of x cubed, 3x squared. And now we're going to see if we can substitute again. Let's see if we can substitute. If I substitute 0, I get 1 over 0. That is not indeterminate. 1 over 0 approaches either positive infinity or negative infinity. Okay. Actually, any constant over 0 will approach one of the two infinities. One thing to be aware of. The only thing that you need to decide now is positive infinity or negative infinity.
Positive, because the zeros going to the right. I mean, the right.
Well, let's take a look. Cosine, the graph of cosine looks like, not like that. The graph of cosine looks like this. Okay, now to the right, cosine is positive. So we're going to go to positive. On top of, let's take a look at the graph of 3x squared. 3x squared is just a parabola, no need to glorify it. To the right of 0, it's positive. So we got a positive function on top of a positive function. That tells me that the result will be positives. If the result is positive and we're going to infinity, that means we're going to positive infinity. That's it. Okay, that's 7. Whoa. 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 Why isn't it working? Why is the touchscreen not working? Okay, let's move on to question, or I don't know what question we're going to go to. Did we? Oh, we should do 8, huh?
Yeah.
Yeah, we should do 8. Let's take a look at 8. Depending on how things go, 8 may be the most difficult one we do after school. So we're taking a look at limit as x approaches 0 of 1 over x squared to the x power. Now I have a faint recollection of doing this in one of the classes. We did it in first. Did we do it in fifth? Okay, so let's do this now. Notice we have x to the x, or we have an x exponent here. So we have to figure out, is this indeterminate? Of course, 1 over 0 goes to infinity. So this looks like infinity to the 0 power. So we have to decide which one grows faster, 1 over x squared or x. Or which one is more dominant. Okay, so we take our y. Y is equal to our function, 1 over x squared to the x power. We take a natural log of both sides. We simplify the right side a little bit too. 1 over x squared is x to the negative 2 power. Then we apply a limit. So the limit as x approaches 0 of the natural log of y is equal to the limit as x approaches 0 of, let's take that negative 2 and shove it in front. Negative 2x natural log of x. Now, I think I said this in period 1. This is not something you have to do, but it will make your work 3 times easier at least. Okay. All right, let's check for indeterminate. X is going to 0, so this is negative 2 times 0 times negative infinity. Yeah, that's definitely a disguised indeterminate form. We need to, this is the key, we need to turn this into a form that we can use L'Hopital's rule on. So let's get it to that form. The limit as x approaches 0, keep that negative 2 with a natural log of x. I think that's a better place for it. Over 1 over x. And let's check. Can I use L'Hopital's rule on that now? Let's see, that numerator is infinity, the denominator is infinity. Yeah, I can use L'Hopital's rule now. Okay, so now we use L'Hopital's rule. Take the derivative of the numerator and denominator separately. The derivative of the numerator is negative 2 over x. The derivative of the denominator, negative 1 over x squared. Oh, I remember messing this up in period 1. That's right. That's equal to the limit as x approaches 0 of 2x. There's no reason I can't just substitute now. That's equal to 0. So what have we proven? We've proven that the limit as x approaches 0 for the natural log of y is equal to 0. If we exponentiate, then we've also proven that the limit as x approaches 0 of y is e to the 0. And if we substitute again, then we see the limit as x approaches 0 of 1 over x squared to the x power is 1. So, great work. So that's number 8. Number 9 is a reverse situation. We did that in period 5. We didn't do it in period 1. We did it in period 5? We did it in period 1. We didn't do it in period 5? What are we doing in period 5? I swear we did a lot in period 5. We did a lot in period 5.
14, 10, 3, 21, 20.
That's a lot.
That's a lot from like those sections.
Don't go off that screen.
All right. How's the pizza? Good? Do we need to do number 9? Period 5. Do we need to do number 9? Yes. Okay, let's take a look at number 9. Actually, let me check if the Google Hangouts is still working. Still working. You know, I bought the touch screen because I thought I'd be able to use the touch screen, but this is so much easier for me. This does, you can't see what you're writing. Come on.
Oh, really?
Yeah, you're right on it.
Because who put these on for me? No, it was Jessica. What's Jessica's last name? When he went to UCLA. Jessica Quachi. Quachi put those on. So now I have to keep them on forever because now I'm a Quachi. Huh? You have Chem with Quatch? Yeah. Quatch. Oh, Quachi. Okay, what are we on? Number 9. Like half of these things here are from like other students, and I don't have the heart to get rid of them. Like one of this is from Lena Core. No, the red gnome is from Teresa Kim.
Where's the Georgetown gnome from?
Georgetown gnome is from Doris. Doris's last name. Doris's last name. I don't remember. I see her on my Facebook every now and then. Okay.
The emergency center.
I don't know. I forgot who put that up. Number 9. Limit as x approaches 0. As t approaches 0. 1 over sine t minus 1 over t. Okay, so this is an indeterminate form. This is actually the indeterminate form infinity minus infinity, which doesn't really seem indeterminate because we like to think that infinity minus infinity is 0, but it may not be 0. We actually don't know if this infinity here is bigger than this infinity here, or if this infinity is bigger than this infinity. We don't know which infinity is bigger. Does that sound crazy? Which infinity is bigger? It's supposed to. Have we talked about Hilbert's Hotel? Some infinities are bigger than other infinities. So imagine that there is this is from a mathematician from the early 20th century named Hilbert, David Hilbert. Imagine that there's a hotel. It has an infinite number of rooms because of the conventions in town, obviously. Infinite number of rooms, the conventions in town, all the rooms in this infinite hotel are taken up. Okay. Okay. Infinite number of salesmen are in the infinite number of rooms. All of a sudden, some guy comes in late and said, sorry, I left the iron on, I had to come late. Says, I need a room now. And the innkeeper says, you know what, this may be an infinite hotel, but all of the rooms are taken. Says, and then the guy says, no, you don't have a problem. All you need to do is tell the person in room 1 to go to room 2. Tell the person in room 2 to go to room 3. Tell the person in room 3 to go to room 4. Everybody just moves down 1 room, and I'll just sleep in room 1.
Whoa.
Everyone has to.
So as you can see, that second infinite number of rooms is bigger than the first infinite number of rooms. But it gets even better. What if an infinite number of salesmen come? Okay, we have an infinite number of rooms with an infinite number of salesmen in them. Infinite number of new people come. There can't possibly be any more room. But there is. All you got to do is tell the person in room 1 to go to room 2. Tell the person in room 2 to go to room 4. Tell the person in room 3 to go to room 6. Double your room number, go to that new room. And all of a sudden we have an infinite number of new rooms.
Whoa.
Yeah.
What if you want to find the average person?
What do you mean by the average person?
Wouldn't we be dividing the infinite amount of people by five?
Well, I mean, there's the practical way to answer that is if each person has one, if each room has one person in it, then even if it's infinite, the average should be 1.
There's one person.
One per room.
It's indeterminate, there is no average.
But if you could always have one room, then the amount of rooms would be larger than the amount of people.
Yeah, or not.
I guess that would mean that there are a finite number of people that aren't.
Okay, let's get back to this one. Again, we need to find out which infinity is bigger, the first infinity or the second infinity, or we need to find out if these two infinities are the same size. Okay. All right, so this is not an indeterminate form that I can use L'Hopital's rule on because I don't have a numerator, I don't have the denominator. So the way to do that is to algebraically give ourselves a numerator and denominator, which means that we need a common denominator. Oh no, I'm still on the, darn it. Limit as t approaches 0, t minus sine t on top of t sine t. Okay, so now I've created an indeterminate form where I can use L'Hopital's rule. And that's the key. Get yourself to an indeterminate form where you can use L'Hopital's rule. Now we take the derivatives. Limit as t approaches 0 from, no, t approaches 0. The derivative of t is 1. The derivative of sine t is cosine t. The denominator is a product, so use a product rule. 1 times sine t plus t times the derivative of sine, which is cosine t. And let's check again. Equals 0, oh boy, over, oh no, 0 over 0. So use a stronger L'Hopital rule, do it again. I don't know why they call it the stronger form of L'Hopital's rule. It just means do it again. Okay, the derivative of 1 minus cosine t, sine t. The derivative of sine t, cosine t. The derivative of t cosine t is a product. So the derivative is 1 times cosine t plus t times the derivative of cosine, which is negative sine t. Okay. And now let's check, is this indeterminate? Oh boy, it's a 0 on the numerator. Oh, but it's 2 on the denominator.
Yes.
Not indeterminate, the limit is 0. Thank you. Oh, that I wrote a cotangent. Sorry. That's cosine t. I can see how that's confusing. Okay, any questions on 9? Okay, 10, 11, do we need to do those? Okay, let's go. Yeah, we do have 10 in class. Let's take a look at 11 for now. Which one grows faster? Which one grows faster? X or X1, X plus, ugh. X or X plus 1 over X? What do you think? I don't know. Let's just compare. I'm going to put the gnarlier one in the denominator. X over 1 plus 1 over X. Okay, how do I deal with this? Well, probably the bad thing to do right here is just to take L'Hopital's rule, because you can simplify this, right? Yes, you can. This is the limit as x approaches 0, x on top of x squared plus 1 over x. You can simplify that too, right?
Yeah.
That's equal to the limit as x approaches 0 of x squared on x squared plus 1. You don't even need L'Hopital's rule. Limit's 1. Same rate. Same rate of growth. Yeah. You were worried about taking a bunch of L'Hopital rules, weren't you?
Yeah.
It's 22.
So the powers are the same. And
We get
it's
two
zero,
on
zero.
Yeah.
So same rate of growth could be any number except 0 and infinity.
Any number.
But 0 and infinity, then either f or g.
Okay. We've got a few of these to do from 12 to 17. So 12, I think we had interest in one of the classes. We should look at 12. 12. And before we do 12, I want to just look at the antiderivative. That might be helpful if I work that out ahead of time. Yeah.
For number 11, why did we do the limit as x approaches 0, and then for 10 we did the limit as x approaches infinity?
It should have been infinity. It's not infinity?
Oh, that's right.
Oh, yeah, that's supposed to be infinity. I don't know why I wrote a 0. Okay. Take a look at question 12. If I want to integrate this, I'm going to need a technique. U substitution, no. Integral by parts, no. This looks a lot like a partial fraction problem.
Yeah.
That's exactly.
That guy likes partial fractions. 2 over x, x minus 2 equals a over x plus b over x minus 2. I always try and write down an answer key here. That means 2 equals x minus 2a plus xb. If x equals 0, then we get a equals negative 1. If x equals 2, then I get b equals 1. So what does that tell me? That tells me that 2 over x squared minus 2x, that's going to be equal to 1 over x minus 2 minus 1 over x. Note that I cleverly turned them around. That means the antiderivative of 2 over x squared minus 2x dx is equal to the antiderivative of 1 over x minus 2 minus 1 over x. Okay. So what is that? That is the natural log of the absolute value x minus 2 minus the natural log of the absolute value x plus constant, which is the natural log of x minus 2 over x plus constant. Perfect. We needed that. Because now if I want to put limits there, and I do want limits, limits are from negative infinity to negative 2. That's just going to be the limit as a approaches negative infinity. Natural log of x minus 2 over x from a to negative 2. Now I've taken off the absolute values because if we think about this, we're always going to be dealing with negative numbers. And the numerator here will be negative. The denominator here will also be negative. Negative over a negative, that's going to be a positive. So I don't need the absolute values actually. Let's substitute. This equals, where's my cursor? There we go. This equals the natural log of 4 over 2, is that 2?
Yeah.
Minus the limit as a approaches infinity of a minus 2 over a. Sorry, negative infinity. I did forget the net. Ooh.
Could you keep it as ln x over x before you did that? Like take away the negative 2 because of the...
I probably wouldn't do it that way. Okay, so the natural log of that. Let's talk about what's going to happen here. Okay. Now, it doesn't, I mean, the natural log, we're going to apply it after the limit. So really, what's going to happen here is we're going to do the limit first, and then we're going to do the natural log. Basically, the only thing that needs the natural log is this part, a minus 2 over a. What is this limit? It's definitely 1. And that's done. Natural log of 1 is 0, of course. Any questions on 12? Yeah.
Honestly, the guided test answer is not just not the one for two. Oh, I see.
Okay, that takes care of number 12. Last questions on 12. I'm going to move on. Should we do 13?
Yeah, sure.
Okay, 13. Let me check and make sure we're still recording. I think we are.
There you have the whole story of the hotel too.
Yeah, that's cool. I mean, a total of like 10 people would watch it, so it's cool.
Any former students watch your channel?
No,
Why?
they're done with my shenanigans, right? Although sometimes you get like a random person watching it from who knows where. That happens a lot with statistics. Apparently there aren't a lot of good statistics teachers out there. It's kind of sad. Let's look at the antiderivative first. I think I like that method. What is the antiderivative of x e to the 2x dx? Okay, can I use a u substitution? This really is a tabular method, but I like to troll you all with it. Okay, so this is a tabular method, u dv. Let's see, we have an x and an e to the 2x. The derivative of x is 1. The antiderivative is 1/2 e to the 2x. I should mention again, one of the common mistakes is to take derivatives of both sides here, and that's fatal. Okay, so the antiderivative is 1/2 x e to the 2x minus 1/4 e to the 2x. Or if you prefer, 1/4 of 2x, no, 1/4 e to the 2x, 2x minus 1. That's my antiderivative. Okay, we've worked that out. Let's work out the integral now. Negative infinity to 0 of x e to the 2x dx. That's going to be the limit as a approaches negative infinity. 1/4 e to the 2x, 2x minus 1 from a to 0. Substitute 0, I get e to the 0 is 1. 2 times 0 minus 1 is negative 1. So I think I get negative 1/4. Help me out if I got that wrong.
No, you're good.
Good? Okay. Minus, now we have a limit. Limit as a approaches negative infinity. And boy, do I have a bad feeling about this. 1/4 e to the negative 2a, no, to the 2a. (2a minus 1). Okay. What is this limit? Okay, well, you know, one thing that might give you problems is this negative infinity. So let's deal with that a little bit differently, okay? Rather than looking at going to negative infinity, what if I change that as a going to positive infinity? What would I have to do? And let's change that. Let's say u goes to positive infinity. Wouldn't that have to change to negative 2u?
Mhm.
Wouldn't this have to change to negative 2u minus 1? Let's put that together. Limit as u approaches infinity, that is negative 2u minus 1 over 4 e to the 2u. What is this limit? Yeah, it's indeterminate. Isn't that infinity over infinity? Negative infinity over infinity. Okay, we use L'Hopital's rule. I really hope you could just look at that limit and know what it is. Negative 2 over 8 e to the 2u. What is that limit? I mean, the numerator is staying constant, the denominator is growing. That limit is 0. Okay, so what have we shown? we have shown we're getting -1/4 minus 0. What's the antiderivative? -1/4. Am I close to writing? Oh, yeah, that's good. Yeah.
Can you explain how we switched the negative?
We kind of substituted where u is equal to -a.
Okay. So everywhere we have that, we just put.
Yeah. And basically, it's easier to think about things going to positive infinity than it is to think about things going to negative infinity. But if you look at it from up here, I mean, I can kind of tell from here. This 2a minus 1 is going to stay on the numerator. But this e to the 2a is going to move to the denominator since the exponent is negative. Okay. Once I figured out I have e to the 2a in the denominator, I know that e to the 2a grows a lot faster than 2a minus 1. So this was going to 0 even without using L'Hopital's rule, just a kind of reasoning through the relative rates of growth. Yeah.
At the beginning of the problem, instead of the integral from -infinity to 0, could you do the integral from 0 to infinity?
No. Changes it completely. Okay, any questions on 13? Good. We did 14 in period 1 of the classes, right?
Yeah.
Yeah.
You in both of them?
You can do 17.
Oh, okay, 14. Is 15 okay?
Yeah, can we do 15, please?
Prioritize and go to 15? Sure.
Can you explain where we realized we need to do the U substitution?
Right at the line, first line.
Right, but because isn't e to the infinity, like why can't you just take the derivative of that?
On 14?
Yeah.
Why would I take the derivative of it?
For L'Hopital, doesn't it doesn't it become infinity over?
Well, we're not trying to find the limit, we're trying to find an integral.
Okay. Okay, so L'Hopital is only for limits, not for integrals. Thank you.
I mean, you could use an integral. I mean, the integral could be in L'Hopital's rule. But, I mean, the whole reason we use L'Hopital's rule is to solve a limit. We're not, strictly speaking, we're not trying to solve a limit with 14. We're trying to solve an integral. So we wouldn't go to L'Hopital right away.
Can you take the integral of e to the 1 over x without a U substitution?
No.
Because of like the inherent chain rule of the 1 over x?
You're saying the integral as written?
As if it was just e to the 1 over x, could you take the integral?
Could not take the integral.
Because of the
1 over x.
the 1 over x.
Yeah.
Because that needs its own. Got it. Thank you.
Okay, so we're prioritizing. You guys are calling an audible and you're going to question 16. Does that sound about right? You want to do 15? That is not a straight line. Okay, so let's take a look at 15. 15 is pretty quick. No worries about 15. We're going to take an antiderivative of dr over 4 minus r square root of.
For 13, can you just, in the beginning, can you just do e to 2x divided by 1 over x? Would that still come out to be the same answer?
You don't have a reason to do that.
Okay, it still would be the same.
It's just that that's the kind of thing you would do for L'Hopital's rule. And there's no reason to use L'Hopital's rule here because we're not taking the limit.
Okay.
L'Hopital's rule is only for when you want to take a limit. Now, it may happen that you're going to need a limit for your integral, but the big process that we're doing is the integral. So don't do L'Hopital right away. Okay, so integral here, this is, well, I think it's probably better for us to rewrite this as 4 minus r to the negative 1/2 power doctor. Have a good day. The way to integrate this is with the u substitution. U is 4 minus r. Du is negative dr, or dr is negative du. And that changes this integral to u to the negative 1/2 power negative du. Antiderivative of u to the negative 1/2 is 2u to the 1/2. We have this negative, so negative 2u to the 1/2, or negative 2 root 4 minus r. That's my antiderivative. I forgot a plus constant, but that's not going to be important. Here's my antiderivative. Now that the antiderivative is in place, I can go ahead and do this. 0 to 4 of dr over root 4 minus r. That's going to be equal to, well, we got to figure out which one of these two are actually giving me the problem. Is it the 0 or is it the 4? It's definitely the 4, the upper limit. So we're going to take a limit as b goes to 4 of negative 2 root 4 minus r from 0 to b. Let's make our substitutions. We now have the limit as b approaches 4 of negative 2 root 4 minus b minus negative 2 root 4 minus 0. We are almost finished. Okay, is there any reason I can't substitute 4? Not at all. What's 4 minus 4? 0. Good. This is 0 plus 4. Done. Questions on 15? Will it let me Yes, it will. Am I still recording? Yes, I am. Yeah.
Why are you saying that the 4 is a problem?
The 4 is a problem because I get a 0 on the denominator.
But doesn't it not matter because that's the 4 you have to plug it in? So that's the integral. And when you take the integral, then it's
It turns out that it's not a problem after I integrate. Okay, a lot of us want to see 16. So again, we're going to look at the antiderivative. Let's start with factoring. Or let's start with the antiderivative and factoring. Let me write down the problem first. 1 to infinity dx over 1, 7, and 12. Okay. Let's go ahead and factor. That's 3 and 4, right? Set up our partial fractions. Let's go ahead and take a look at the numerators. Let's pick some values. Let's say x equals -3. That means I get 1 equals 1a. A equals 1, right? Let's say x equals -4. We get 1 equals negative b. So b equals -1. Oh, I did it right. That's good. Okay, so 1 over x squared plus 7x plus 12 is equal to 1 over x plus 3 minus 1 over x plus 4. Antiderivatives. Antiderivative of dx on top of this guy. We'll do the antiderivative of this, x plus 3 minus 1 over x plus 4 dx. Antiderivatives. Natural log of the absolute value x plus 3 minus the natural log of the absolute value of x plus, not 3, 4, plus constant. Lastly, we're going to simplify. That's x plus 3 over x plus 4 plus constant. We're going to leave it here for just a second. I feel like I write better with this pad. Yeah. Probably because I've been using this pad for like 8 years. Even though I can't see what I'm writing, I write better with this.
Or you get used to it.
Hmm?
You get used to it.
Yeah, you do. It definitely helps my eye-hand coordination. All right, you ready to finish? Never tried. Is there a PC version of Fruit Ninja? Is it on the Windows Microsoft Store? Fruit Ninja. Oh!
Then you have to like stare at the TV as
You know, don't stand by me.
Why not?
All right, I'll do that later. I may have found a reason to have a touch screen again. Okay. Cats?
Cats playing Fruit Ninja.
Cats playing Fruit Ninja?
Oh shoot, we are not done. What am I doing? Ah. Okay, so the integral from 1 to infinity. From 1 to infinity of dx over x squared plus 7x plus 12. That's equal to the limit as b approaches infinity of the natural log of x plus 3 over x plus 4 as x goes from 1 to infinity. Great. I don't need the absolute values anymore because we're dealing with only positive values of x. Why did I write an infinity there? It should be a b. This is equal to the limit as b approaches infinity, natural log of b plus 3 over b plus 4 minus the natural log of 4/5. Okay, so what is this limit? Natural log of infinity over infinity, sure. What? Natural log of 1, yeah? Now you should be able to know a couple of different ways why that's the natural log of 1. First of all, L'Hopital's rule tells you that that's the natural log, that limit is 1. Second of all, the lead terms, b over b, simplifies to 1. That should tell you.
Also, like an infinity, 15 and 4 are smaller than version.
Sure, I feel uncomfortable with that method though, because what if it was 3b?
So we don't need to show any work with like.
No.
We can only use the power rule if the limit at x approaches infinity is actually approaching infinity, right? That's the.
One more time?
So if limit as x approaches infinity, we just use the power function, right? The lead term.
Lead term test, yeah.
Yeah. So
You're right.
that's the only.
Yeah. Okay, can we talk about this just one more, a little bit more to do? We have negative natural log of 4/5. That's equal to the natural log of 4/5 to the negative 1 power. And that's the natural log of 5 over 4.
Or it could just be natural log of 1 over 4.
Yeah, it's the same.
It's the same thing.
Yes. Okay, so that's 16. I am finished with 16 now, right?
Yeah.
Great. Okay. I think we did 17 in both classes. What did we do in period 5?
Like 6 problems and 2 facts.
We did like 6 problems.
Which six?
Like in period 5, we did.
19, 22, 21.
Yeah. 12. Did 19. We did 19. No. 3. I don't know. Okay, so let's take a look at number 7. I think you want to see 17. Let's take a look at 17. 17, again, we're going to take the method by looking at the antiderivative. Let's start with the antiderivative of x squared e to the negative x. Start with that antiderivative. Okay, so this should tell you integral by parts. This should tell you tabular method also. Looking at this, you should be able to tell that that's what we need to do here. Okay, derivative of x squared, 2x. Antiderivative of e to the negative 2x. Sorry, negative e to the negative x. I don't know why I said 2, sorry. Derivative of 2x. Antiderivative, e to the negative x. Derivative of 2. Antiderivative. Great. Let's put it together. We get negative x squared e to the x, negative x, minus 2x e to the negative x, minus 2e to the negative x. Simplify. Looks like I could factor out a negative 2, right? No, a negative. Let's just factor out the negative. Negative e to the negative x, giving me x squared plus 2x plus 2. We're going to have to compute a limit, so that negative exponent needs to go by. This is negative x squared plus 2x plus 2 on top of e to the x. Sweet, that's my antiderivative. Let's take a look at the integral now. What we want to integrate is from 0 to infinity. And we need to go from 0 to B. Take a quick pause here to let you guys catch up writing. Catch up. Check my cats. Do I have any good cats? I'm one rare cat away from getting them all. I got one. No, I have Frosty. I'm missing, what is it? Ame-san? Oh, Lady Meow Meow. Xerxes. I see her, she shows up, and then like I never. Okay, I think we're ready to go. Let's substitute. I've filled the food dishes for my cats. This is a limit, no, yeah, the limit as b approaches infinity of negative b squared plus 2b plus 2 on top of e to the b minus, which is plus 2 over 1. Sweet. Hey, what is this limit? Okay, at this point, I really think you should be able to look at that limit and know what it is. It's 0. We have the numerator growing at a rate of x squared. We have the denominator growing at a rate of an exponential rate. Clearly, the denominator is growing faster than the numerator. This is going to go to 0. We might as well satisfy the skeptics. Negative 2b plus 2 over e to the b plus 2. Limit as b approaches infinity, that's negative 2 over e to the b plus 2. And that is just 2. Thank you. Cool. We're done with that. 17, toast. Is there anything else you want to look at?
Like just the preliminary, like deciding if we thought it would converge or diverge, but like we never went through.
Okay. Mm-hmm.
How we got to the third line was yeah.
From here to here? L'Hopital's rule.
Where did we start?
Well, we did L'Hopital's rule twice. We started here, took the derivative. We got here.
Okay.
Took the derivative again, we got here. You know, I would not have complained if you just went from here to 2. I mean, if I'm doing my job right, you should be able to look at that and say that limit is 0. Okay. Okay, 2 more to go, and then we're gonna call it a night. Let me check if Mrs. Freya texted me or not. She probably didn't text me. Oh, I never looked at Gold Star. Oh, Cream Sun is on in my cat yard. Peaches. Peaches is in the orange cube. Okay. Okay, take a look at 18. And we need to get some kind of a sense whether or not 18 converges or diverges. What do you think? Yeah, converges is a good idea. Why do I think it converges? X squared in the denominator, yeah. Numerator is more or less constant. The denominator goes to 0. Okay, so that means I want to find a bigger function that's going to converge. So let's start off with 2 plus cosine x on top of x squared, just x squared. And we need to find a function that's bigger than that. So how do we find a function that's bigger than that? Well, I can make the denominator smaller, but there's not a whole lot of simplifying here with that denominator. It's already x squared. It's already as simple as it gets. Or I can make the numerator big. How big could that numerator possibly be? 3, right? That numerator is always going to be less than or equal to 3. Okay, so let's make the numerator 3. Let's make the denominator, keep the denominator x squared. So 3 over x squared should always be bigger than 2 plus cosine x over x squared. So the integral from pi to infinity of 3 over x squared dx should always be bigger than the integral from pi to infinity of 2 plus cosine x over x squared. That should always be true. Hmm?
How did we get 3 again?
Cosine, the biggest it could be is 1.
Oh.
Antiderivative here is negative 3 over x. Okay, does that make sense? Let's substitute. The limit as b approaches infinity of negative 3 over b plus 3 over pi should be greater than equal to, gets tiring writing this same integral over and over again. Especially when I forgot the dx every time. Damn it. No dx. Okay, what is this limit, 3 over b? 0. Good. So this integral has to integrate to something that is less than 3 over pi. 3 over pi is a little less than 1, right? It's like 0.9 or something. Now, I remember when I was in high school, my calculus teacher used to say things like that. 3 over pi, that's about a little less than 1, like 0.9. I used to go, how does he know that so quickly? Then I realized he was just bullshitting every time. I don't know that it's 0.9. I'm just guessing it's 0.9. Is it 0.9? What's 3 divided by pi?
That would be about 0.9549.
No, that was bad. 9.5?
Oh my God.
Come on. 9.5. Okay. So does this integral converge or diverge? It must converge. Integral must converge. Okay. If there's no, there's no way that this integral could diverge if it has to integrate to a number smaller than 0.95. That might be one of us, right? Maybe someone left behind their phone. That happened yesterday. Sweet. Okay. And last question 19. Was it one of us? No. So for 19, we have natural log of x over x. And we need to decide converge or diverge. Look at the denominator. Diverge. Okay, so we need to find a smaller function that diverges. Okay. So how can I make this into a smaller function that diverges? Well, I could modify the denominator, but the denominator is already natural log, or the denominator is already x. Not much I can do there. Or I can make the numerator smaller. Okay. Well, once x gets big enough, the natural log of x is always bigger than 1, isn't it? If x is big enough, the natural log of x is bigger than 1. Good. That's my function. 1 over x. Denominator is the same size. The numerator is bigger. It's a bigger function. Okay, let's look at the integral. We're going to integrate from, I don't remember, is it 1 to infinity?
Yeah.
1 to infinity of natural log of x over x dx. That's going to be bigger than this integral. Honestly, at this point, we've done this integral before, haven't we? We know that this diverges. We have done this integral before, right? So look at the result we get. We're saying the natural log of x over x dx should integrate to something that's bigger than infinity. So it has to be infinite, right? If it's going to integrate to a number that's bigger than infinity, it's got to itself be infinity. Therefore, diverges. We've done this before. That's it. Yeah.
Okay, so you know how you found a function smaller than this problem, the last one you found that is bigger.
Yes.
You know when to do it.
That's why you have to start off by having that gut instinct.
Okay. So
If the gut instinct tells you converge, find a bigger function.
What if you guess wrong?
If you guess wrong, you're going to get inconsistent results, and you start all over again. Don't guess wrong. It should be fairly obvious which ones converge and diverge at this point. I mean, Reminds me of that. Do you ever watch that 80s movie, like Better Off Dead? Where the guy says, "How do I ski?" And then the girl says, "Go that way, real fast. If something gets in your way, turn." You're welcome.
Can I ask you